All right. So what do we want to talk about today? Yesterday we got up to looking at linear transformations. We formally developed, uh, spent a full lecture on linear transformations and computing linear transformations, seeing how these work. We showed that every linear transformation can be written or any linear transformation is essentially a matrix. There is always a matrix associated with a linear transformation in finite dimensions. Infinite dimensions, things get weird. So if you're curious about that, if any of you guys have to keep taking higher math, or if you're physics, if you're going to grad school for physics, you'll get into tensors and tensor products. Those are generalizations of matrices, really. And they're going to be more useful as soon as you work in things like Hilbert space, especially if you're a physicist, you will work with Hilbert spaces, infinite dimensional spaces, and you'll need to generalize those and understand, well, how do I actually find what a matrix should be in infinite dimensions? Of course, we can't build an infinite dimensional array. At least you kind of can, but you would have to develop the mathematical rigorous tools. But for this class, finite dimensions, your first course in linear algebra, we have nicely shown that all linear transformations are matrices. And hopefully you kind of got the idea that linear transformations, they are the functions we want, right? I kind of started the lecture with, really, we want to study functions. That is a lot of what math is about. We have different types of spaces and structures, and a big way of how we study these spaces and structures is we look at how functions behave. What type of functions do we want to look at on these spaces that respect the structures? So let's give today's topic a title. So first thing we need to address, we'll pick up where we left off. I'll kind of continue with where I was going. But we need some properties, and then we're going to develop linear transformations. Forgot this. Let's call it linear transformations 2. Because we got a little stuck yesterday. We want to study these functions on spaces, and so we've hopefully developed a better geometric intuition for vector spaces. And I kind of was mentioning this a lot yesterday, that vector spaces are all flat. And in low dimensions, we understand what a flat space is. A straight line is straight, it's flat. A plane is flat. So you kind of want to think about that in higher dimensions as well. Locally, a typical local three-dimensional vector space is flat. Nothing is bending. So if you want to kind of compare that to something like a black hole, right? A black hole, they often draw like gravity wells. Since I know some of you guys are like astrophysics, sometimes they say, here's space-time, and then here's a black hole, and it just drops, and then we have this singularity. It's not entirely a great accurate representation because, of course, a black hole exists in at least three-dimensional space. And so really what you kind of want to think is like with planets and black holes and stars and stuff as this massive object sitting in space, and what it's doing is all the space in 3D around it is bending towards it. So it's a bent space, it's a bent 3D space. So the spaces around black holes and planets, because of gravity, is bent. It's a bent 3D space. But that's something we don't have to worry about. That's something you'll get into with differential geometry. Linear algebra, all we want to work with are flat spaces. But of course, if you are an astrophysicist or thinking about taking some more math classes along those geometric lines, the reason we're studying flat spaces is because even in curved spaces, well, if you look closely enough at a curved space, we are sitting on the Earth, for example, right? And if this Earth is a gravity well bending space around it, even locally, right, in our natural neighborhood, in your room is a flat geometric space. It's a 3D space you can move around in, and you're not really being affected by the bent space locally in your region. And so even in curved spaces, a lot of the ways we study these higher complex geometries is we look into these local properties and look at, well, close on small intervals and small areas on these geometric objects, we can model them by these flat spaces. And so linear algebra is intrinsically tied to differential geometry and to a lot of geometry. So it's a big topic and why we study it in and of itself. So our linear transformations then are these special functions that we found that preserve this notion of flatness, right? We've really found that a linear transformation, we'll say from Rn to Rm, is going to have the property that it preserves linear combinations. So namely, any scalar multiples of any vector combination, typically our vector combination, a linear combination of our vectors, the vectors are chosen from either a linear independent set or a basis, if we want it to be more rigorous, and that our linear transformation is going to preserve this structure. Namely, I can perform the linear combination of all of these basis vectors and then apply the linear transformation, or we can apply the linear transformation to the bases vectors and then after that we can perform the linear combination, multiplying by the scalar multiples and then adding them all up. And yesterday we realized if we are given a basis, then with respect to this basis, if we know how the linear transformation acts, namely if T of Ej is equal to, we'll use the letter A1 J E1 A and J En. Let's see, did I do that right? I don't know if I did. Did I? That should be, yeah, I did do that right. So this is me asking myself if I did it right. As I was saying at the beginning of class, the hardest thing about linear algebra sometimes when you're doing your work is making sure you're keeping the indices and like the order of things correctly. So if we have a linear combination, right, the linear transformation, it's going to send some vector Ej into, I guess if we're going to use m-dimensional space, let's go up to m dimensions. In other words, we're writing each one as a sum of the basis vectors. This E1 to EM are going to be our basis vectors for RM. And from this, we can create the matrix. And so A, this pen might be kicked. This matrix that we make out of these scalars is going to be our matrix associated with T. And really it defines all of the operations on T relative to these choice of bases. And so where we left off is, well, what's going to happen when we change our bases? So to make a few notes, I am going to use maybe slightly different notation than the book. I am going to always use E as kind of our standard bases. And I was mentioning yesterday how no matter what choice of bases we choose, the basis is always looks like a standard basis relative to itself. So it kind of doesn't matter what we call like the first basis we want to start working with might as well be the standard basis. Because this, even if I had a different basis, if I used different letters, use a V, V1 to Vn as our bases for our domain for Rn, we would still get, these constants might be different, but when I make the matrix out of those constants, that matrix will still be associated with T, and maybe we say relative to the basis E. But even if I chose different basis elements, since we're kind of now looking relative to that basis, those basis elements relative to themselves look like the standard bases. Does that make sense? Maybe we'll explain it. I'll keep talking about this. This is going to be a big theme throughout this lecture. And especially as we get to change of bases and now how would the matrix change and how do we compute how the matrix would look differently with a different choice of bases? How do we shift from one basis to another is the big question we kind of left off with yesterday. So that's going to be what we're exploring today. Before we get into that too much, we're going to need a few properties that we kind of left off, but not big. They hopefully will seem pretty intuitive. Excuse me one second. Let me blow my nose. Namely, we're going to need composition of linear transformations, and that's going to tie into matrix multiplication. The book also, there's a couple of like properties. It has like a specific section that it calls like properties of linear transformations. It's not very long. Check it out if you want. It's not even really needed to. The key thing is this property here. This is our key defining property of linear transformations. And that's how I defined what a linear transformation was. The book, I don't know, I think it kind of like lists it as a separate property or as like a theorem from some other things. We're going to keep this one. That's the most important thing. And even from this property, we can actually deduce some other things that the book lists. So if we want to just write them out real quick, I'll let you guys check them on your own. Namely, that if T is a linear transformation, then it's always going to preserve the zero vector, which is needed. As we kind of seen, our vector spaces always pass through the origin. So not only are they these flat spaces, but they have to cross the origin, right? Lines through the origin, planes through the origin. And so if we are going to transform these spaces, we need to respect that. So T of 0 has to go to 0. You can actually check this and deduce it from a linear combination. Just do T of 0 plus 0. Well, that's going to have to be T of 0 plus T of 0. And you can kind of deduce where this 0 has to go. And you can show that it has to go to 0. There's no other point it can go to without breaking our defining property. The other thing they mention is that it's going to preserve negatives. Namely, if I take a vector and we flip it in the opposite direction with a negative, that's the same as just applying the transformation and then flipping it in the opposite direction after the transformation. Again, this is going to be a property that we can deduce from the defining property. So nothing big there, but let's take a look at composition and what's going to happen with that. So just like with functions, we can compose, and I'm not sure how much you guys really got into sort of the algebraic theories of functions and how they behave. You've seen it all, but this is probably one of your first math classes after calculus. So probably the last time you really tried to take a look at functions abstractly, but probably back in linear algebra. So you're only doing it at a linear algebra level. But with matrices, we're kind of first now introducing this notion, a new notion of multiplication. Right? Matrices are kind of the first mathematical structure that we see where multiplication is a little bit different. Namely, we have seen that matrix multiplication is not necessarily commutative. Still has the distributive laws, associative laws, all that good stuff, but it's not necessarily commutative. So it's not just like multiplying numbers like you've probably seen in all your other math classes. And the other thing you can kind of get, well, is from calculus, if you have functions, there's a lot of operations you can do on functions, right? I can add two functions. We can multiply two functions, right? Calculus, you've got your product rule if we had to take a derivative of this guy. We've got rules if we got to take a derivative of this guy. But then we also had this other operation, and namely composition. Where composition, we have to have that the image of G lands in the domain of F, and then F will send the image of that to the image of F. And so I claim that function composition is a type of multiplication. Namely, like addition is addition in terms of its algebraic structure. There's not much different between different types of addition. Even if we're adding, these are functions that we're adding, versus if we are adding numbers, there's not much difference between how it ends up being computed, right? Here we just add, well, on the evaluations. So for linear transformations, this will help maybe give a better example as to why composition gives us this type of multiplication. Multiplication you can kind of think of as, well, your intuition for multiplication, but also the way it behaves with addition. It should have this distributive property. And this is exactly what we're going to see for linear transformations. So let's say we have T going from RK to RM, and then we have S going from RM to Rn. If we have two linear transformations, then the composition S composed T is going to give us a map, a function from Rk to Rn is a linear transformation. So we can compose linear transformations. The composition will still be a linear transformation. Moreover, if, let's say, A of T and let's use B of S are the associated matrices, then the associated matrix to S composed T is given by just the product of the matrices. So this is, we can list this as a theorem or a proposition if you guys want, whatever level of importance you want to associate to this. It's fairly big. I don't want to go through the proof. How would we prove this? We do have this theorem that two linear transformations, I think we have this. I don't know if we stated this. Let's rewrite it in case we didn't. Proposition or theorem for two linear transformations, T and S, from Rn to Rm, let's say Rm to Rn, if T of V equals T of S, or S of T of V equals S of V for all V, then T equals S. I don't even know if we want to list this as a proposition or just like a defining characteristic, right? If two linear transformations act the same on every single vector, then they are the same linear transformation. That's essentially all it's saying. So, of course, how would we check this? We would want to check that all the vectors that this guy could act on are going to be exactly the same as how this guy acts on the vectors as well. So to chug through that proof, you could actually come up with, come up with the matrix associated with T, come up with the matrix associated with S, chug through some of the computations and kind of show why they're exactly the same. Go through some of that work, maybe look it up in the book, or I would recommend maybe try to work it out yourself, or at least justify it to yourself as to why. If I have T of V, how is T going to act on V? Well, it's going to be the same way as A acting on V. And so the image vector is going to be exactly the same. And then S is going to act on that. And the way S acts on that is going to be the same way as B acts on the other image. You could probably get it a little quicker without getting too tedious with the computations, but try to justify that for yourself. So a few questions though, since we're talking about functions and operations on functions, right? Since we now know that linear transformations are the transformations we like to study, this brings up a little bit of a question of, well, how do we create new functions? Hopefully you guys saw this in your calculus programs, in your pre-calc programs as well. We start with these function building blocks, then we build broader arrays of functions by performing different operations on functions. Namely, we add functions, multiply functions, divide, subtract, of course, and then composition is in of itself a completely separate operation than our standard arithmetic operations. And so, at least from this, we kind of see that in this case, function composition results in a type of multiplication. So our question we want to, of course, ask is, well, how does it behave with addition? But I guess first we should ask, does addition even work with linear transformations? What about this guy? This is kind of going to be our odd one out. So maybe I'll leave this to you guys for homework, or if we have time, maybe we can come back and address it. I don't want to get too much into that because I want to leave space for the main topic of our lecture, and that is change of bases, change of coordinates. There's also a little bit in the book about special transformations in R2. So maybe we'll get to those as well. So just some questions for you guys to ponder and maybe work out for yourself. If we have two linear transformations with the same domain, can we add them? So if I take two linear transformations, does that define a linear transformation? Are we preserving this linear transformation property? Does this function still preserve linear combinations? And of course, the way this is defined, S plus T acting on a vector V, would be take S of V and then add, T of V. So I'm trying to see if you guys can play around with that. That one should be pretty easy. Hopefully you're getting an idea of yes. Why might this be yes? The other kind of follow-up to this would be, what about the associated matrix? And in this case, hopefully your natural guess would be that if we have this as a linear transformation, then maybe the associated matrix would be just the sum of the matrices, is how that should work out with the structures involved, but we would have to show it and demonstrate it. That's where our first guess should be to check. And then our follow-up question would then be, well, what about multiplication? If S and T, I guess we should specify, S and T were linear transformations from the get-go, but we need to know, can I add two linear transformations and still get a linear transformation? Our previous property says if we start with two linear transformations and can compose them, then composition itself is a linear transformation. But what about products? So if we have Rm to Rn is a product of linear transformation, namely where the product would be S of V times T of V. Noted inflection on my voice. What does that even mean? Does this even make sense? What do I mean by times? So think about it. Can you make sense of it? Or what's the big blaring problem? Namely, T of V is going to be a vector, S of V is going to be a vector. Well, now I have a multiplication. What should this multiplication operation be? Should it be a dot product? Is there some other product? If we take a dot product, then we're certainly not going to land in an n-dimensional space. We'll just land in our scalars. And then the question is, well, what would be the associated matrix? So maybe by taking a look, trying to answer those questions, hopefully you'll get a sense of why that doesn't quite work. So there's not really a sense of multiplication of linear transformations, that the real multiplication structure, the real multiplicative structure, is actually composition amongst our linear transformations. So enough with some of the abstract theory. Let's get back into our change of bases. So our primary thing we're going to use is namely that if we have a composition of transformations, then it just corresponds to our matrix multiplication. So let's take a look and go back to our associations with linear transformations and bases and the matrix associated to those. And well, let's see what happens when we have a change of bases. Oh, one more thing. We need to talk about inverses. Just looking at my outline here. Since we have composition, we can now get we can now get inverses. So suppose we have T from Rn to Rn, T and S. So their square, their matrices will be square matrices, are such that when we take their composition and act on a given vector, we get back that same vector. And that's the same actually. So since they operate, the domain and range are the same, we can compose in either order And primarily, if we compose in either order and act on any vector, and what we get back is that same vector, then S and T are inverses of each other. This, hopefully, you gain from your intuition from calculus when you have functional inverses. Whenever you learned your trig, all the trig that all students know and love, sine, cosine, tangent, and then you find the inverse trig functions, arc sine, arc cosine, and all those. Really what we're trying to do is undo the operations of the function. Not always the case. We can't always undo the function, but you kind of want to think of a function as like a sequence of mathematical operations. And so the inverse of a function undoes that sequence. If a function multiplies by 2 or takes a number, squares it, then multiplies by 2, we want to ask, can I undo that? If I do that operation, and then can I apply another operation that will undo that and get me back the original number? Can't always happen. And same thing with linear transformations. So linear transformations, we have this idea of now a matrix. It's really just a matrix multiplication where it's going to shift, stretch, and twist our space based on the basis vectors to give us a new space, or at least kind of morph a given space into a different linear space. And so our question is, can we undo that? This is the operation of the inverse of linear transformations. So we usually write, as you guessed, t with an upper script -1 for the inverse of t. And if you had to guess, what's going to be the associated matrix? So if A of t is the associated matrix to t, then the inverse matrix is the associated matrix to t inverse. And this follows from the fact that matrix multiplication corresponds to composition. So if we need a linear transformation that undoes, that composes in such a way to undo a given linear transformation, well, then the matrix should multiply to undo the associated matrix to that transformation, or the inverse matrix will multiply to undo that operation. It will give us this identity operation. It will send every vector to itself, not change it when we compose. Okay. So let's get back to change of bases. So suppose we have our standard bases. We're always going to start with our standard bases again, because the thing you are first looking at is kind of what's defining the coordinate system. I mentioned yesterday, or maybe the lecture before, of how when we are defining new bases, it's really just like looking at the space with a different coordinate system, and you can draw different grids. So in some sense, you kind of have to think, well, if you have absolutely no notion of what the space looks like and have no grid on it, as soon as you put a grid on it, you can always kind of change your reference frame in such a way that it looks like a standard basis. I wish we could be maybe in person, so like we could draw some pictures or kind of illustrate that a little bit better. But take my word for it that whenever you're starting, whatever your starting basis is, wherever space you're at, the basis you're working with from that frame looks like the standard basis. So we have E is our standard basis. For Rn. And now let's say we have a different basis. Then we typically like to write each of these vectors in terms of whatever basis we've started with. So we often have each of these basis vectors written as a linear combination of the standard basis. So I'm going to use C for our constants here. So it's going to be C1 J E1 plus C2J E2 plus CNJ EN. So even though we have a new basis, since the previous set of E's was also a basis, we can write each of these elements as a linear combination. Then what we can actually do is just like, well, when we define linear transformations, we kind of take a look at what happens with a linear transformation acting on a vector. Saw it expand out into a linear combination. And, well, what did we do with that linear transformation? Well, we have these doubly indexed set of scalars, set of coefficients that we can form into a matrix. So what we can look at is this matrix of scalars, C11, it's going to go up to 1n, it's going to be a square matrix, Cn1 up to Cnn. Sorry, that's nn, not, man, and I wrote it again, sorry. The subscript there should be 1n. It looks like m there. This is a matrix. So the coefficients that we get from transforming these basis vectors B into a scalar combination, a linear combination in regards to the basis E, we can actually think of itself as a linear transformation. So I'm going to call this, it's going to be a little weird for the notation, but you'll see why. And we'll talk about it and try to make sense of it as to why this is. This is going to be called CB inverse. And really what we're doing when we have one basis written in terms of another basis, you can think of this as transforming our space. So we're still working with Rn, but I'm going to introduce, and I'm going to use subscripts on these now. So Rn, the capital N, or the upper script N, gives us the dimension. I'll write as the subscript what our basis element or our basis set is. And so this is going to give us a transformation from the basis B to the basis E. And this might seem a little backwards, so maybe let's do a concrete example. See if I have one written. I don't think I have one written, but we can just kind of make one up here. So, example. Let's just work with R2 and Our standard basis, of course, is just going to be 1, 0, 0, 1. And let's come up with a new basis of 1, 1. And let's do 1, let's say -2, just to change the numbers up a little bit and scale things a little different. So of course we have R2 here with a basis B. And so what we want to think of, the matrix CB is going to be a change of basis from RE, R2 basis E, into R2 basis B. This is a linear transformation that changes the basis from E to B. Conversely, so there is a theorem, I kind of just glossed over that a little bit, but the theorem is that if I change a basis, since we're changing one basis into another basis, we're not losing any information, right? We're mapping the full space of R2 onto the full space of R2. We can undo that process. We're not losing any dimensions. We're not doing anything weird, especially since we're working with bases. And bases, as we've learned, generate the entire structure of the vector space. So take my word for it that these operations are invertible. And so CB inverse, what's that going to do? It's going to take the basis B and map to the same space, R2, but with our basis as E. And so our question is, well, how do we build those matrices? So it's fairly clear. We want to, let's go ahead and name and order things. So it is typical if it's not written, use lowercase letters for whatever the basis is called. So of course, that's going to be our E1, that's going to be our E2. And of course, the order is preserved. We do want to keep track of the order. So this will be our B1, this will be our B2. If it's not written, it's safe to assume that that's fair labeling if you want to use letters to represent them and vectors instead of having to write it out. So for example, it's pretty clear that B1, we have our linear combination. It's just going to be E1 plus E2. And likewise, our linear combination for B2 in terms of the basis E is going to be E1 minus 2E2. And so if we put those scalars into a matrix, namely we're putting the vectors B into a matrix. Now keep in mind these are vectors B, but as they are written, they're written relative to this basis E. So we kind of think as E is our standard starting basis. And when we write things like 1, 1, 1, 2, and create this matrix, the reason why it corresponds to changing the basis B to the basis E is you kind of want to think of both where are we starting and where are we landing. Since we have B written in terms of these basis vectors E, this is kind of where we end up. It's like kind of the final information that we're given. If we start in RB, what happens when I multiply this matrix by this vector, by our what looks like the standard basis element? Well, we've got to be very careful because this vector is actually B1 It looks different though. Why does it look different? Because we are starting with our basis B, right? So if we're just starting with R2 and our basis was B, B1 looks like one linear combination. It's one multiple of B1, 0 multiples of B2. And then where is this going to end up? It's going to end up as 1, 1. But again, what is this guy now? This is B1 in reference to the basis E, sorry, capital E. Right, so since we're ending here and we want to end in this format, the reference basis of how this vector is written is relative to the basis E. Does that make sense? This can be a little confusing with like the directions and like which direction, how we're sending which basis to which. The big takeaway, or at least one big idea that might help you keep this straight, is that change of bases transformations don't change the vector. They change how it looks. Since the reference i.e. the basis changes. So whenever you're working with these CB matrices, CB or CB inverse, always just think whatever matrix, whatever vector we're acting on is the same vector we end up with. So this vector and this vector are the same, they just look different. So how does it look in this basis? It looks like 1, 0. One combination of B1, 0 plus 0 multiples of B2. Where's it going to end up? It's the same vector, but now we're writing it in terms of E, which is going to be 1 times E1 plus 1 times E2. So does that make sense? Looks like Mackenzie asked, is this matrix CB or CB inverse? So as I was just saying, the matrix we've got, this is CB inverse. Real kind of confusing as to where we start. Always think about kind of where you're ending up. And like if we act this matrix on what looks like a standard basis on 1, 0, it's going to naturally pick out that first column. And if we pick out the first column, well, this is vector B1, but we're writing it in terms of the standard basis of E. So the image is E, and the domain is our B basis. And so naturally, of course, if we want to find CB, we would compute the inverse. I can just write that there at the bottom. We would compute. Why can I not spell correctly today? Compute the inverse of that matrix. So we'll do some computations like that. Let's kind of tie everything together and bring in linear transformations, and then we'll work through a few examples. Okay, so suppose we have a linear transformation T from Rn to Rn. And I'm going to now write our basis subscript E1 and E2. So again, if we're kind of just starting with a linear transformation, every basis we sort of start with is going to look like the standard basis in that reference frame. So not only is the domain basis going to look like E1, but wherever we end up, the way we write vectors in column vector form is going to be relative to whatever standard basis we're working with, or whatever basis we're working with, which looks like the standard basis in the image space. And I guess we can change the dimension here, Rm to Rn. So it doesn't necessarily have to be square. And then suppose we have different bases. We'll say B1. Do we need to write it out? Let's not write it out. We'll write it out in examples. B1 for Rm, and then B2 for Rn. Our question then is, how do we represent our transformation relative now to those different bases? And of course, represent it as a matrix. Right, as soon as we have a linear transformation, so we want to use the same letter t. T itself is abstractly just a function between Rm to Rn. So it kind of doesn't matter what the bases are. The linear transformation itself is always going to be a linear transformation. But these matrices that we associate to the linear transformation, well, this is why we've been using different letters. We don't really want to define the matrix itself as the linear transformation, because we got to be a little more specific than that. The matrix itself that we come up with is the linear transformation relative to the choice of bases. As soon as we have a different set of basis vectors, we're still going to have the same linear transformation. It's going to behave the same on the same vectors. However, because we've changed our reference frame, we've changed how the coordinate grid looks on our vector space, well, now all the vectors are going to look like different linear combinations, and the matrix, or the way the linear transformation acts, is going to look differently in matrix form. So the matrix representation, to summarize, of a transformation depends on the basis. So naturally, we're almost always starting with a linear transformation, and we're given information about how it behaves, how it acts on a given set of vectors. From that, we can kind of deduce a matrix form for it. But as soon as we do that, that essentially dictates, the choice of bases that we've started with, which again always looks like the standard basis. And so now our goal is, well, if we can do that, we can at least get that piece. We know how to find the matrix of a linear transformation because we're always starting with standard basis vectors. But now if we want to apply a transformation, a change of bases transformation, and now see how the matrix, or yeah, how the matrix would change with respect to a different set of bases, we don't want to start over from scratch. And so the question is, can we use these transformations, perhaps these change of bases matrices that we were just introducing, together with the matrix information for T to get a new matrix for T relative to a new set of bases? And so of course we can, and the process actually becomes much simpler because of our tools of matrix multiplication. So the diagram looks like this. We start with Rm, and I can simply just transform it with respect to T. Or of course we could call this maybe AT, and that's our matrix associated with T with respect to our standard basis. Well, from the standard bases, we can change into a new basis with our change of bases matrix, or our change of bases transformation. And then from here, what do we want to do? Well, now we want to perform T again. And we are running out of letters. I think the book calls this M, B2, B1. Let's keep it with the book notation, just to keep it standard, so that way you guys aren't seeing a lot of different notations that mean the same thing. So this MB2B1 is going to be the matrix associated with T with respect to our bases B2 and B1. And forgive me, that should be an N. And then, of course, we also have a change of basis matrix in the image space. And so the idea is that we say that this diagram commutes. We put a little circle in there, meaning that it should be the same, that if I start off here and I apply the linear transformation, and then change the basis to basis B2, it's going to be the same as if I change the basis first to B1, and then apply the linear transformation that corresponds to the same linear transformation with respect to the starting with the basis B1 and ending in the basis B2. So in other words, let's actually get a different color here. Since these are invertible, so the change of basis matrix, we can go in the opposite direction. So this is CB1 inverse. Likewise, we have a CB2 inverse here. So in other words, if we want the matrix associated with T between the bases B1 and B2, well, since these guys, they are isomorphisms. I'm sorry for using that word at the moment. We will talk about what isomorphisms mean. We should be able to get to that tomorrow. But they are invertible operations, change of bases. So in some sense, if we want M, B2, B1, we need to start here and end here. Start at Rm, B1, end at Rn, B2. Well, instead of just applying the transformation, it should be the same as changing the bases back to E1, applying the transformation we know and love, and then changing the bases to B2. So we can write that out now in terms of composition. We are simply just composing linear transformations between different target, between different domain and image spaces. So what do we want to compute? We first need to go backwards, right? Since we're starting here, we have to go back to basis E. So the first thing we're going to do is go back to our basis E. Then we're going to apply our transformation T. And then we're going to change the basis to B2. So that is our big result. So this is how we do change of bases for a transformation. And I guess instead of T there, we could have had the matrix. Since M is a matrix, think of that as AT, the matrix associated with T with respect to our standard bases. So any questions so far? Okay, let's do some computations. Let's keep that diagram handy. I definitely recommend keeping it handy when you're doing computations so you can kind of tell where you're at. And maybe, and actually might be better to fill in the values for R. So suppose we have T from R2 to R2 given by T of AB is just BA. So it flips the coordinates. And so we're just in R2. I'm just going to keep R2 here. And then what do we want? So find the matrix of T associated with different basis vectors where our B1 is 1, 0, minus 1, 1, and B2 is 1, 1, 1 minus 1. So all we got to do is just compute all the pieces. So here's our formula. We need CB2, the transformation associated to T in standard coordinates, and then the inverse of CB1. So the hardest part is going to be that guy. But all of these, again, not too hard, but now we're doing kind of all of the matrix operations we've been doing, the row reductions, the inverses. We're doing it essentially 3 times. So let's go through that. A of T, easily enough, we should be able to deduce the columns. So just for some scratch work, of course, what's T of 1, 0 going to be? It's going to flip things. So it's going to go to 0, 1. So that should be our first column. Likewise, T of 0, 1 is going to flip. So it'll go to 1, 0. So that's an easy one. Matrix associated with T, not too complicated of a linear transformation. And now remember our CB1 inverse is there. And so let's label the vectors. Let's call these guys B's, B1 and B2. Unfortunately, since both of the bases have the letter B, maybe you just want to choose different letters. So I'll call this one V1 and V2 for the basis in B2. So we know that B1 is just E1. B2 is negative E1 plus E2. Now, of course, we're putting the coefficients into columns. So if we take that basis B1 and make a matrix out of it, this corresponds to the change of basis to B1 in reverse. Careful with that inverse there, right? And just remember, again, if I act on 1, 0, it's taking the vector B1, and then its image is going to be E1. I guess in that case, since they're the same, it's a little hard to see. If I act this on the vector 0, 1, it'll pick out this column, which is going to send the basis vector B2 relative to itself is 0, 1. And then it's going to change B2 to this form of B2 in reference to the E basis. And then, so of course, our last one is CB2 inverse is going to be our basis B2 written out in terms of their coefficients. So we will just make a matrix out of that, 1, 1, 1 minus 1 for our columns. So these two pieces, easy to work out. Of course, you do need some sort of description of the transformation to come up with its matrix. In this case, not too bad. This one, easy to work out. As soon as I have a new basis written in terms of these standard bases, we just make column vectors out of them. And we got the inverse of the change of bases. Of course, what do we need to do with this guy? I need to invert this guy to get the change of basis for the E's in terms of B2. So let's go through that real quick. We've got 1, 1, 1 minus 1, and then append by a identity matrix. Row reduce until we get an identity on the left. So 1, 1, 1, 0. Let's go ahead and subtract those guys. 0 minus 2 minus 1, 1. We are going to divide by 2. Do we want to divide by negative 2? Yeah, let's go ahead and do that. So it'll be 1/2 here and negative 1/2 here. Row 1 didn't change. And then negative row 2 plus row 1. So 1, 0, 0, 1. And now what do we get? So if I have negative 1/2 plus 1 will give us positive 1/2 here. And then positive 1/2 plus row 1 will give us a positive 1/2 again. So there's our matrix. So our CB2, 1/2, 1/2, 1/2, minus 1/2. Luckily, 2 by 2s, not too bad. And then our final answer, so let's get back. Let's just write it here. I think we've got space now. So since now our MB2, B1 is going to equal CB2, 1/2, 1/2, 1/2, minus 1/2, times our linear transformation, times our CB1 inverse. Now all we got to do, matrix multiplication. Let me leave some space here. I think we can squeeze it in. Let's keep this guy and multiply the second two first. Just a bunch of ones. So first row, first column gives us a 0. First row, second column gives us 1. Second row, first column gives us 1. And then second row, first column gives us -1. As we should expect, right? This matrix did just flip the columns. And then now when we multiply these two, what are we going to get? So 1/2. And then first row, second column, we've got 1/2 minus 1/2. We're going to give us 0 there. Then we've got 1/2 minus 1/2. And then we've got 1/2 plus 1/2. So it looks like a 1 there. And that's our matrix. Any questions on that? All right. How you guys feel about this? Did you guys catch it all? Seem hazy? You guys need some time to kind of sit with it? Some of the theory, I think, can get a little hard to follow. Again, the hardest thing is keeping track of these change of bases formulas and understanding which direction, which bases we're changing from and to. So keeping track and keeping those straight, real important, because if you do one in the wrong direction, it'll throw everything off. Any questions on that? You guys want to see another example? Or I think I want to touch base. Let's touch up on special transformations in R2. So we'll take a little bit of a break. This is kind of a little more theory intensive. Computations, if we did 3x3 matrices, it would get a little more intensive, of course, finding some of these change of bases and the inverses to that. 3x3s we've seen can take a little bit more time. So maybe we take a little bit of a break from some of the deeper theory and go to special transformations in R2. And maybe if we have time, I don't think we will, maybe we'll talk about complex numbers. I'd like to kind of just throw the idea at you about complex numbers. We're not going to cover it in this course, but I know since a lot of you guys did say your astrophysics, or astrophysics and some computer science majors, I think we had in the class too. Computer science, maybe not so much unless you have to take like an electrical engineering or a circuit course. Astrophysics, you're going to want to learn complex numbers at some point in time for sure. Especially if you have to get into relativity, complex numbers are going to come up, or if you even get into like quantum stuff, any quantum mechanics, got to know complex numbers. And we can actually use matrices to represent complex numbers, which is kind of interesting. So I kind of just like to throw the idea at you. And then if you guys are curious about it, take a look at the section in the book on it. We will be skipping that in general, though. So in regards to our geometry, we have what are called Euclidean transformations. These are angle and distance preserving. Angle and distance preserving transformations, and we'll stick with our plane. So Euclidean geometry developed, ancient Greeks by Euclid kind of formalized everything. And it was all about planar geometry, flat spaces. So we have this now language of vector spaces and linear transformations that we formalized to describe transformations on these flat spaces. So now we can kind of tie these ideas together a little bit. So the idea is if we have, curves in the plane or shapes in the plane, whatever there's an intersection, we have a certain angle that these two curves are going to intersect at. And so while I might morph the space and morph the curves, I don't know if I'm going to do this appropriately. Let's say they flip upside down and do something like that. And now that intersection point is over here. The angle between them should be preserved. And likewise, the lengths of the curves should be preserved. So a distance preserving. So hopefully in Calc 2, you learned how to compute things like arc length. Likewise, if we just had geometric shapes, some triangle in the plane, it might flip and rotate and shift, but it's still going to be essentially the same triangle. So it's kind of been a task of mathematicians to describe these. How do I, if we, ancient Greeks studied all sorts of triangles, circles, shapes, and then to build on that, well, how do I know if two triangles are exactly the same? After we've introduced a coordinate system and a grid, if I have two triangles somewhere in the space, how do we know if they are exactly the same triangle? Well, this was kind of all the theory of Euclidean transformations. So to summarize the results that we found, a Euclidean transformation is going to be a flips over a line. It's going to be a rotation of the entire plane, right? So I can take this whole thing, rotate it. That triangle is not going to change. It's not going to stretch, skew, anything like that. It'll still be the same triangle with the same measurements, the same angles. It'll just be moved to a different place. And then the other thing we can do are translations. So let's take a look. What's a flip going to do? Well, I could take this whole thing and flip it over the vertical axis or the horizontal axis. And you can kind of tell from that, well, again, the shapes are going to be preserved. All the angles, all the lengths of the side lengths of the shape, nothing's going to change. It's just going to flip upside down and move down here. Translation is as well. If I just take everything and shift it to a certain point, nothing's changing. Angles are staying the same. Side lengths are staying the same. Now, the problem is, well, what's going on with the translation? If I take this whole space and just move it to the right, so is the origin. So translations, unfortunately, don't preserve the origin. However, if you can imagine the rotation, origin doesn't move. Since we're rotating about the origin. Likewise here as well. Since any line we're going to flip over, I really mean we're going to flip over a line through the origin. And actually what we're going to reduce it to, we only need one flip. All we have to do is flip over the x-axis. Flipping over any other line is actually going to correspond to rotating and then flipping, and then maybe rotating back. So it's these two we want to take a look at for this course. We can model, that pen is cooked. By linear transformations. And you can kind of imagine by the geometry, since they're preserving the origin, well, if they're preserving the lengths and the distances, they're not doing such a complex transformation that all of the vectors now in R2 are simply going to be rotated, and it's going to have this linear transformation property. Namely, it's going to preserve scalar multiples and linear combinations of vectors. So how do we deduce these? Let's say we rotate by an angle theta. So we have our unit vector. Here's our E1 and our other unit vector pointing upward. Here's our E2. If we rotate by an angle theta, I'm just taking every vector and rotating it theta radians. So what's going to happen? Here's our E1 angle theta, and here's our E2. So the angles are preserved with this, so there's still going to be a right angle. This is still going to be a basis. Let's call this specifically, say R of theta. If you guys can see that, maybe I can draw it bigger. So our rotation transformation applied to E1 and our rotation transformation applied to E2. So E1 is going to go to this vector, E2 is going to go to that vector, and they should be the same size. Still going to meet at a right angle. And moreover, since this is a Euclidean transformation, I didn't stretch anything. The distances are preserved, meaning the lengths are preserved. How long are each of these vectors? 1 unit. So if they're 1 unit and we rotate them, where are they going to end up? Somewhere on everyone's favorite object on the unit circle. Yeah? So that angle there is theta, and the angle here is the vertical angle with the vertical axes. We rotated both of those guys theta, and since they are of unit lengths, they should be on the unit circle. And so what are the coordinates going to be? Unit length, horizontal component is going to be cosine theta. Vertical component is going to be sine theta. In other words, r theta of E1 is going to go to cosine theta in the x direction, sine theta in the y direction. What about the other vector? Well, we got to be a little careful because the angle here is a little different. So r theta acting on E2, well, this distance, theta, if theta is just, let's say theta is only between 0 and pi over 2 at the moment. Well, this distance, if I take sine theta, E1, gives us the correct length of that. However, since we started vertically, we're now going in the negative direction. So we need a minus sign there. The vertical component, though, is going to be cosine of theta. So that might be like our first guess. It seems to work for small rotations of angle theta. Do some little geometry, maybe some extra drawings, and then justify that that's still going to hold as we rotate around. And that minus sign, as theta increases here, we're still going to want the minus sign in quadrants 2 and 3. But then as theta gets bigger than pi, what's going to happen to sine? Sine will switch signs, and then it'll take care of that sign as well and make the overall expression positive and give us a positive horizontal component. So this is our matrix. In other words, or our coefficients, our matrix of a rotation by angle theta. We list now as columns. So it's going to be column, right? E1, E2. So it's going to be cosine theta, sine theta, minus sine theta, cosine theta. So that is our rotation matrix. Let's do our flip matrix. So I'm just going to call that F. So of course we look at our standard bases, E1 and E2. And let's say F is going to be our flip about x-axis. So of course a vertical flip. So what's that going to mean? That means F of E1 not going to do anything, right? That's just going to stay as it is. But F of E2 is just going to go to negative E2. In other words, F of 1, 1 or 1, 0 equals 1, 0. F of 0, 1 just goes to 0 minus 1. And so we got an easy matrix for that. Our flip transformation corresponds to 1, 0, 0 minus 1. And so, homework, maybe check other vectors for both of these transformations. See how this matrix is going to act on the vector 1, 3. Does it flip the matrix over the x-axis, or that vector over the x-axis the way we think? It should. So just check that and check the computations and make sense of the matrices. But we now kind of run into an extra question. So what about, let's call it F of M equal to a flip over a line of slope M. The book gives a formula for this, but they don't tell you where it comes from. But I think you guys will be able to figure it out. It's not too bad. It's a little bit of trig. We don't have time to go through it today, so let's just kind of outline what's going on. It's a bad coordinate, but let's say we have this line. Where our slope is M. How do we find the matrix for it? I claim that what we can do is, first what we can do is rotate by an angle of negative theta. We can then flip over the x-axis and then rotate back. So what we would need to do is, for a given line of slope M, we need to figure out this angle. We can take this line and take everything in the plane and rotate it so that that line is now on the horizontal axis. Now flip everything and then rotate everything back. That would be the same as flipping values over that line. Everyone see that? And so what we would do is just do a little bit of trig and realize that the ratio of the side lengths is going to be m to 1. And so namely, we have this tangent of theta is going to be our slope, change in y over change in x. And so tangent of theta is m. We can model this triangle like we do with a lot of pre-calc trig problems. And now if we have our r thetas, we have the formula for r thetas are cosine theta, sine theta here. So let's write it out. We're going to have r of theta will be cosine theta minus sine theta, cosine theta. Our flip, as we saw, is just the identity, but this coordinate's negative. R of minus theta, this is another good homework exercise to work out on your own. If this is r of theta, homework, r of negative theta should be equal to the inverse matrix. If I rotate by a certain angle and then apply a transformation and rotate in the opposite direction, should not change anything, should give us back to where we started. So those should be inverse operations of each other. Try to show that if we put in a negative theta here and for sines and cosines, and then multiply those two matrices, we get the identity. You might have to remember a little even and odd functions about your trig. So I'll let you work that out, but I gotta tell you what it is here. Of course, cosine of negative theta is cosine. Sine is an odd function. So it's going to actually just flip that minus sign. So this is what FM should be. Work that out, and now you can actually work out the identities as well. That cosine of theta from our little trig diagram, cosine of theta is going to be 1 over square root of 1 plus m squared. And sine of theta is m over square root of 1 plus m squared. So if you multiply everything out, I mean, I guess you could substitute first if you want to substitute all your sines and cosines, or you can multiply everything out first, use some trig identities to simplify it if you see any, and then substitute. And then you'll arrive at a formula for flipping across a line of slope m solely in terms of the value of m. Good little problem to work out. The formula is there in the book, so check the answer and check yourself and check your work and see if you can get to that from this computation.